Well, good morning, dear. Welcome back. So you have started watching videos on Introduction to Machine Learning, and we are discussing back propagation algorithm. Today we are going to digest the concept of back propagation algorithm by implementing it in a two-input XOR pattern, right? So we want my network should um, learn the XOR pattern for two input, one output uh, data set. Okay, let's see. So, but before that, you know that earlier what we discussed, the back propagation algorithm follows, these are the steps. Step 1, initialization. Set all the parameters, including the threshold, that is also a parameter, but the associated input is always we take -1. Okay, that's the only difference, because we want something to be, some signal to be deducted from all the ACFC. Okay, so you have inputs, you have inputs, you have inputs, and all the summation. Okay, and then -1 times W0, and then we want that it should go to the transfer function. Okay, sigma kind of transfer function. Okay, and then you get output. So that's the reason we attach a fictitious feature which is -1 for threshold. So threshold parameter also is kept as a weight parameter. Okay, so and initialize them. How to initialize? Within selected some range you fix up and randomly choose the values. Then we need to, of course, before that we need to fix the architecture itself, so that how many inputs are there, how many hidden layer, and how many neurons in the hidden layer. So all this my decision. You see, it's a design. That's why it's a design, right? So and slowly, when you become skilled, then seeing the problem, you will be able to design the network itself, right? Some thumb rules are there. Say, for example, if the nonlinearity is not so much, in the sense that you have a continuous nonlinear function, then you can use one hidden layer. If you have discontinuous nonlinear function, then you could use more than one hidden layer, 2, 3. Okay. So more nonlinearity, more hidden layers. Okay, hidden layer basically trying to learn the representation which is hidden in the data. Okay, so next step is activation. Right, so you have selected all my neurons. You know, are nothing but a logistic unit. Okay, a logistic regression unit. So which you have used in logistic regression. So you can use that activation. That means activate the back propagation neural network by applying all these inputs to the desired output. Okay, and that's the sigmoid function uh, which you fed with all weight associated with input minus the threshold. Okay, so this is in the hidden layer. Uh, Actual outputs calculation of the hidden layer. Then actual output calculation in the output layer. So you will have to just YKP. So IJK. So this is here. Here you are trying to figure out. So sigmoid summation, all for a particular neuron, all this one, this one, this one, this one. Okay. So m number of inputs are coming over here. That has to be summed up and minus W0K. So we are keeping this notation. That means threshold. Okay, for the kth neuron. That has to be the used as an input in the sigmoid function. Okay. Then weight training, as we just told you, that two weight training. One is calculate error gradient for the neurons in the output layer. So this is the way error gradients, simple way we have calculated earlier. And then once you have error gradient, then you use for error weight correction jk for particular epoch p equals to alpha. Alpha is the learning rate as usual. It could be 0.01 like things, okay, times yjp, that is the input, okay, which is output for the jth layer, okay, input for the kth layer, times delta kb. Clear? Okay. So then you can calculate the weight parameters in the next epoch. Wjk equals to earlier epoch wjk plus delta. This is delta learning rule. Same we are following here. Okay. Then calculate the error gradient for the neurons in the hidden layer. So for hidden layer, I need to, since these are all also contributing to the error, so I need to multiply this by summation of all the wjk, okay, which is actually contributing to the error. So this will be our, so this simple uh, the error gradient at the output layer times this factor, okay, because I am propagating only these together with this, okay, this is already known, fine. So calculate the weight correction then, same, okay, and then iteration will continue epoch by epoch, okay, increase p by 1 and go to the state 2, that is again activation, and repeat the process. How long? Say till here the error which is not equals to say 0.001. So I will have to give a threshold that if error, because error will never be 0 exactly, right? So you need to have a stopping criteria of the iteration. So you can see, you can tell your program algorithm that when the error at the output layer becomes 0.01 or 0.01, 0.001, it depends on how much accuracy you need, okay, and how much um, computation you want to spare, because more stringent threshold, for example, error equal to 0.001 will require more computation than error if you stop error equal to 0.01. And if it solves your purpose, you do it. You set the computation always, okay. So that's the back propagation algorithm, and then I will digest it by repeating each and every step by taking a small problem. So we have two input. So we are solving XOR problem, right? So this is my training data set 0 0 0 0 1 1 1 0 1 1 1 0. So this is XOR pattern, right? And for that, I have decided that I will have only one hidden layer with two neurons in the hidden layer. So, and I have two inputs, right? So here in this generalized neural network, the n is the number of neurons in the input layer. They are two, n equal to 2. Okay, hidden layer is only one, and j, that is in this hidden layer there are m number of neurons, so m equals to 2. Okay, and in the output layer there are l number of neurons, l equals to 1. So n equals to 2, m equals to 2, l equals to 1 in our generalized network is giving me this network. Okay, so now I have just denoted as per this notation W13. So this is hidden layer uh, neuron 3. Okay, so this is originating from 1, so W13, and W14 is feeding the fourth neuron. So here output from this layer. So this is non-computational layer, of course, you know. So from here W23 is going here, W24 is coming over here. So from here W35, okay, and W4 5 5 is coming over here, and this color, purple color, is your threshold. Okay, so this is x0 minus 1 times w03, w04, w05. So how many parameters are there? 1, 2, 3, 4, 5, 6, 7, 8. 8. You can just 1, 2, 3, 4, 5, 6, 7, 8, 9. It becomes 9. Okay. So anyway, so these are my parameters which I need to train. Okay. So this is my data set. So say this is my iteration I am taking. Okay. So x1 equals to x13 equal to x14 equal to 1 for this iteration. That means 1 input should produce output 0. Okay. So x2, 2, 3, 2, 4. This is equals to also 1. So 1, 1. Now, initialization means you will have to randomly select initial weights. Say, this is again some heuristics are there, but you select whimsically randomly. Okay, so don't worry for the beginners. So W13 0.49, 14 0.89, W23 0.4, W24 0.9, 35 minus 1.1, W45 equals 1.09. Then these are our threshold parameters, right? W03 to 0.79, W04 minus 0.1, W05 0.3. So this need not be this. You can select your own. Okay. So we have selected. Say initially these are the values. So all the network parameter now is known randomly, has been assigned a random values like this. Okay. Now, so what we will have to calculate? See, I'll have to calculate Y3, output of this neuron. Okay, Y3. This is Y3. How? Just by activation function, using activation function, which is sigmoid. So, sigmoid activation function we are using. Okay, so all these neurons are my logistic unit. Okay, so we can calculate Y3. How? Just you see, this is my sigmoid function. So this is my summation of xi, okay, xij minus, that is the threshold. So whatever value, now all the values are known to you. X13 is 1, x23 also is 1. Oh, everything is known in terms of a randomly selected parameter. So now you can calculate sigmoid function 1 by e to the power minus wi w transpose x. Okay, you remember? Okay, so say this is, if you have a, so please take your pen and paper, right, notebook now, and do it with me. And so you are getting 0.53. So you have calculator. Every mobile has calculator. Simple calculation you'll have to do. So Y3 is known. Similarly, Y4 is known. Calculate this. Now, actual output of the neuron 5 in the output layer is now I can calculate, isn't it? So these and these are known. Again, activation function is known. This is known. So what is actual output here? 0.51. So what it should have been? 0, because this is XOR pattern which I am teaching. So it should have been 0, but somehow we got 0.51. So error is minus 0.51. So these error will now be used as a raw materials to fix up these parameters, okay, which were selected whimsically earlier. That is called weight training. Okay. Now, what we'll have to do? We'll have to propagate the error. Okay, so calculate error gradient for neuron 5, because error you have calculated here, that only you can do, and that error is now contributed by this and this. So the way they have contributed, I need to compensate. Accordingly, that's why I need to calculate error gradient. That means to know whose role is how much for the error. So rate of change of error with respect to the input, rate of change of error with respect to this input, like that. Okay, that is called error gradient, which we have deduced, right, for in my earlier lectures. So now I will directly use it. So y5 into 1 minus y5 times error. Okay, so this first epoch we're going on. So now everything is known to you. So delta 5, the error gradient becomes minus 0.12. So once you have got, this is very important to calculate error gradient. Okay. So we are all doing at the output layer. And then you can compensate. Take this as a, say, 0.01, okay, or 0.1, whatever. You are doing by hand, so you can take any value. So now um, alpha y3 times delta 5. So alpha is 0.1 you have selected, 0.01 you can also select, and then y3 you already have, y3 is 0.53, so put it here, and then you have just calculated the error gradient, which is here. So you multiply, only multiplication you see. So you multiply and you got the value. Similarly, delta 4, 5. So if this is 3, 5. The way it has contributed, you have compensated, right? This is to be like this. 4, 5 are to be compensated accordingly, right? So this is known, this is the input to this network, to this neuron. This is the input, which is actually Y4. This is the output of the 4 neuron acting as an input to the neuron number 5, and you calculate this one. Okay, you see, they are different, right? And so same way you calculate the compensation. This also has contributed, right, to the error. So it turns out to be this. The moment you got this, so you can now calculate the now you can calculate the delta 3. Okay, you see this step 3 weight correction and the learning rate assuming this. So delta 5 with delta 5. So you have calculated what should be the weight corrections here. Now I need to know also what should be the weight corrections here, right? So that we will do. For that, what you need, you can read on. Initial weights have been put here for your convenience, so you can see. Okay. Now I need to calculate error gradient at this neuron. Okay. So that is delta 3. So it will be y3 into 1 minus y3. Okay. Times that summation I told, summation is only 1 here. So this times W35. Okay. Okay. This is known. Okay. So now W3 is actually, Y3 is known. Everything is known here. And this delta. So W35 you have selected, right? So this is, and then delta 4 is needed to calculate um, compensation of these, compensation of uh, these and this, right? So similar, very, very nice, clean. So having knowing this, now step 4, make weight corrections of neuron 3 and 4. 3 and 4 weight correction, same delta learning rule, alpha times x1 delta 3. So delta W23 alpha times x2 delta 3. So once you know the how the error here is propagated here, then accordingly you can also compensate this and this. So what we have done, okay. So 3 is 3 is being fed by these two inputs. So these two input has actually contributed the error which is here, propagated error which is here. What is the error propagated? Now that error gradient here times what it has contributed. So this is the error propagated. Okay. Uh, so this is very important. This is very important. See, delta 5 is the error gradient here times W35, which is error propagated from here, the resultant error, and that error has been contributed by this and this. So that's the rhythm. Okay. So you need to calculate delta 3, delta 4, the error gradient of this neuron, error gradient of this neuron. Okay. So once you have, then now use that error gradient to calculate that how much compensation has to be done for W13 and W23. How much compensation has to be done for W14 and W24. Okay. And how much compensation in turn has to be done this will be W03. Okay. So sorry for the mistake. So how much compensation has to be done to the we have not shown here. W04 and W05, and their inputs are -1. Here also inputs are -1. Inputs are -1. So this compensation has to be also done in the same way. So all the corresponding to one iteration, we have all the delta W, right? So now we are in a position to upgrade W13, W14, W23, W24, just like adding. Okay. Okay. So you understand? So this is one iteration. So for a particular epoch, there is only one iteration, and you will have to iterate how many times. So again, this you erase earlier W's and replace them by these W's. Okay, these parameter values, and repeat from here again till you are actually calculating the error. Okay, or till the delta 13, delta 23 is not changing appreciably. So this is the iteration, right? One iteration. Then you'll have to come over here, take another data set, and repeat the same thing. Okay, till uh, the error is 0 or near about 0. Then you take this data set, take this data set, okay, and so inside the loop you are for set of parameter you are trying to upgrade this parameter. Okay, so once it is done, this is consist of first epoch. First epoch is done. Okay, then epoch after epoch, you just compensate your again, right, plus delta W. Okay, and you run your algorithm. So is it clear? By doing hand, that how you should know. Final result and testing. So you follow this, and then when to stop. Suppose you give a threshold that when my sum square error, which is a metric, okay, is 10 to the power -3, you can also set 10 to the power -2, so that less number of epochs will be required, and you will get whatever values, parameter value, that is your network parameter. So network is set to be designed. Okay, so This is nonlinear parameter. So directly from this parameter, you cannot draw a decision boundary, but you can test how. For example, this is my XOR. So desired output, these are my desired output. And with this parameter, you are able to calculate actual output at the output uh, layer, right? So you see, although it is not 0, and then we are having some error of these, and you can calculate some square error. So although it is not exactly 0 nearer to 0, isn't it? Not exactly 1 nearer to 1. So this is actually the performance of the uh, network which you have studied, which you have designed. So once the design is complete, you can use it. For what? You can just suppose now these values you are getting from some sensor, right? And you do not know the actual what should be your actual value for this inputs. So you can give 8.7 x1 equal to x1 and 0.99 equal to x2. So you will get some output, right? And you will see that if your design is correct, then you will get equal to, because these are too high, nearer to high, you will get this. So that's the way you can test it. So that's the way the back propagation algorithm works. So you have now known, right? Now you see a lot of calculation, isn't it? Yeah? A lot of computations, but it's easy once you know. So critical thing is at each and every layer correctly to calculate error gradient. Here it is easy to calculate. Here you propagated error gradient, you need to calculate following that formula. Then suppose there is another hidden layer. So from here to here, propagated error gradient you need to calculate. Unless error gradient is calculated, you cannot compensate. So most important thing is to calculate at every neuron, at every level, for every neuron, you need to calculate the error gradient. So that's the trick of back propagation algorithm. So that's it. So few things about neural network. So unlike uh, support vector machine or logistic regression, you do not have a error function like this. Okay, so convex error function is not guaranteed. So not guaranteed. So here the function could be like this. Okay, so this is your J W versus W one parameter, right? So this is error function versus this. So this was for the logistic regression, but this could be for your um, artificial neural network. So yes, there is a possibility that these W's are actually um, are not global optimum value, right? But in actual practice, since it is fully connected, means you are getting a large number of W's. So some W will eventually, so it's just like sand particle. If you have only one sand particle, there is a chance that it could be stuck here. But if you have so many particles you are just putting down there, some of them will eventually go there, and that will be reflected by your metric of error convergence, right? So from practical point of view, that's okay. We are not getting global minimum value, parameter value, but that's okay because it is solving my nonlinear problem. Okay. So one take home is back propagation algorithm is very non-intuitive because the trick is how to calculate the error gradient in the hidden layer and propagate the error from the output layer to the hidden layer. That's the key. Once you can calculate that, you can compensate W. And how long? Till at the output layer error meets your convergence criteria. Okay, and network is designed, and then you can test it. So all the design testing has to be done by label data set. So Again, same thing, you can just collect data, 70% of the data you can use for training, and the rest 30% you can use for testing. Okay, so this is a nonlinear classifier when hidden layers are added. So more hidden layer, more computation. Okay, more possibility that your parameter somewhere will be stuck in the local optima. But since it is fully connected layer, that problem is not very big problem. Okay, um, so it works because you have computation power now. So it will work because more hidden layer means from the input data, more nonlinearity we are capturing. Actually, each hidden layer is trying to extract feature from your input data set. Feature means important part. Okay, and in a reduced way. Input, as many inputs are there, if you have lesser number of neurons, so it will try to reduce from the data. So we can call it that it is extracting feature, and then at the output layer, classification is done. Actually, what is the output you are getting it? So that's all I wanted to convey to you, that using a network, running back propagation training algorithm, you can solve nonlinear problem, classification problem, which earlier by perceptron was not possible. So that's a very competitive um, machine learning algorithm. Okay, with support vector machine and other decision free and all. So this is also very much used. Okay, so this is neural network, and nowadays with deep learning revolution, this and you have tremendous computation power in the form of GPU and all kind of thing, right? You have giant server, so computation storage is not a problem. So as many millions of parameters, if you need to train, it is possible today. Okay, and once the training is over, then of course nothing to be done, right? Very quickly it can be used for classification, right? So it will not take time because all the parameters are set. Only it will give your from your input to an output, right? As per the parameters. So since we have computation power, we have storage capacity, then back propagation algorithm is flourishing. Okay, and this is very much used as a classification tool today. Okay, so with this, I conclude, and I wish you all the best. Stay safe. Bye bye. If you have any question, please come to the discussion forum.